This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hi there, Sergei. Hi. Jamie, nice to meet you. I'm part of the organising committee.
Fantastic.
Yeah, so I think people are still kind of trickling in.
That's right, we can wait.
Was Martin going to give you an introduction?
So the cutoff is what, 2:30?
Yeah, that's when we're supposed to start. But yeah,
Start.
Oh, yeah. So Martin, is there anything you want? I think I'm going to have to do the introduction, but I'm not really sure. Was there anything you wanted Martin to say in particular, or just?
Just my name and everything. Yeah, we can wait for a bit.
Yeah, surely Martin will be coming down.
No, I don't think he is.
Did he tell you to do the introduction?
Yeah, what kind of stuff are you going to talk about then? Learning.
Sergii Strelchuk.
So you're Oxford then?
Yeah, now I'm out. I've been around. Never recorded Oxford.
Oh yeah, so you've been around the UK there.
Yeah, but now it's
Because that's where I did my undergraduate at Oxford.
Oh, right. Which department?
In physics, but
Physics.
Christchurch is my college. I don't know which one you Jesus College. Oh yeah, Jesus College as well.
It's the smallest college, but it's good. Yeah, no, I just started in September.
Yeah.
It's final teacher. I was in Cambridge for like 15 years. And then I was in work briefly and now.
Yeah, which one do you prefer to the Cambridge?
It's hard to know at this stage, but I think they're both very similar, kind of. Basically, collegiate system is all very similar. Slightly different people have different management styles. But other than that, it's just always very.
Yeah. And you know Floyd as well.
Yes, of course, he visited us. Yeah, so he works in the same team, right? I lead the small lead grant.
Yeah.
Cambridge. I still have about 20% of the leadership. Cambridge Rock is obviously the one. Yeah.
I don't know how long we should.
A few minutes.
A few minutes, I suppose. Yeah, have you been to Australia before?
Okay. You see UTS, because like one there.
Okay, wonderful. Sorry. It's floating. Oh yes, it's a great sit. I think it's the coolest thing.
So you did your PhD here?
Yeah, I'm just about to finish. So yeah, I've got an offer.
Martin is on his way now.
Oh, mine's on its way. Okay,
Sorry, can I go?
not mine. But still waiting on him to hopefully quantum research in the Japan.
Quantum. Oh, wow. They're very good, actually.
Yeah, no, it's really great. Because I did like a placement over there.
In the quantum?
Yeah. Although in the London office, it's all the London.
Where are they now? Like in the US?
Yeah. So that's why I'm like basically like this visa thing is so hard to get visa.
Yes, I know. You can apply for O1.
I want, yeah. It's just like it's definitely like 50. Just annoying. Lots of so apparently mine's coming down there, so mine will be able to give the introduction to yeah, just because last minute we realised no one no one knows where the tutorial is. It's like, yeah, probably should be. Yeah. I still don't. I think Mom was trying to do it. She was like, turn around. Oh, but here he is now anyway. So it's all good. You got some. Nice to see you. Hopefully, if I'm not needed on it, I'll sit in if I'm not needed on it.
I need to be in a superposition.
All right. It's a bit of a sprint for you, I suppose. Yeah.
Okay, everyone. Well, welcome to QTML, and it's so great to have everybody here. We're really excited for this conference, and it's just a great pleasure that you've all managed to make it here. So, great pleasure to introduce Sergii Strelchuk.
That's fine.
Why?
No worries.
Anyway, thank you from the University of Oxford, who will be talking about quantum learning theory.
Thank you. Well, thanks. Welcome to QTML, and thank you for having me here. So today we'll have a 2-hour session of, think of it as a kind of as a proper lecture, undergraduate lecture, I suppose. And I'll talk about quantum learning theory. It's kind of the, having seen this, the kind of relatively quick development, and now a rapid development of the field of quantum machine learning, the theory part of it, I found it rather striking that it's not so easy to see how various abstract concepts are motivated. And so the goal of my talk today, our 2-hour session today, will be to try and understand how some of the core concepts in the learning theory. Yes? The mic. Okay, maybe I should sit down. Okay, hopefully that's better. Is there? Oh yeah.
I'd like to wander around too much.
I'll be sitting most of the time, but yeah. I'll just put it this way. So we will. So we'll discuss how some of the core fundamental concepts of learning theory come about, and what significance and role they play in the quantum theory. Hopefully this will be your kind of gateway into understanding some of the most recent results, why they are interesting, why they are motivated in one way but not the other. And I should mention that we will be, I recommend you to take out, pen and paper or a tablet to scribble, even though, you may discard all your notes at the end of the lecture. Sometimes the fact of, writing things down helps a great deal to engage with the material. So the plan for today is the following. First, we'll start by motivating classical computational learning theory. Then we'll introduce main definitions. There'll be quite a few of those, believe it or not. Then we'll discuss how classical learning theory found its way to quantum world. We'll discuss the idea of learning quantum states, why this is interesting. And then we'll discuss general results, but also results that concern a particular family of states, so-called stabilizer states. And then, time permitting, we'll look at learning quantum circuits. So not just static objects, but some kind of quantum evolutions processes. And I'll wrap up with open problems, new directions, and some incomplete but fairly broad list of references that you may want to start studying if you are interested in this topic. I should mention this is not for experts in quantum learning theory or learning theory in general. So if you're an expert, I apologize, but this is going to be very kind of low-key, very basic, at least at the beginning. All right, good. So let's get started. So I will try and move this out of my way. So let's start with the motivation. If there's something that you don't understand, my handwriting is arguably not at its calligraphic best, but hopefully it'll be still legible. So let's start with the motivation. Oops. So when we talk about learning theory, what are kind of the key questions, the key concepts of so-called computational learning theory? So the computational learning theory aims to rigorously define what it means to learn from data. It aims to do this in the kind of the most theoretical way, and in a way that allows us to reason about the capabilities of various algorithms and approaches. So it will give us some precise mathematical definitions, and having precise mathematical definitions or other formulations it will allow us to ask the following and answer the following questions. First of all, we want to understand what types of functions are easy to learn, other classes of functions that are hard to learn. Oops. Perhaps from the learning theory point of view, everything is easy to learn. We will see that's not the case. And we can ask more fine-grained questions as well. How much data is required to learn a function of particular type? And finally, we will be also interested not just in the data, questions about data or statistical inference, we'll be also interested in the amount of computational resources that is necessary and sufficient to learn the function. So what amount of computational resources are required to learn? Okay, so these are kind of the basic questions that surround, that revolve, in this field. And remarkably, all these questions are applicable both to classical functions and to quantum objects, as we will see shortly. To make this discussion a little less abstract, let's try and have a little example in our minds. Let's discuss something called a rectangle learning game. When we when learning these concepts, it's always nice to have something kind of concrete in mind. So what is the setup? So imagine that we are given some points on the plane. It's kind of standard Euclidean plane. And then some of these points, some of which are labeled as plus, or labeled, let's say, positive. So we'll associate them with pluses, and others are labeled as negative. So we are promised or guaranteed that there is an axis-aligned rectangle such that all the points inside the rectangle are positive. So, however, of course, there's a catch. The precise rectangle is not revealed to us. This rectangle is not revealed to us. What's our goal in this game? We want to produce a rectangle, or produce a guess of a rectangle, that is close to the true hidden rectangle. That was kind of used to label the observed data. So let's just draw these points. And let's say these are minuses, these points are labeled as plus. And there is a rectangle, R, that contains only points with the plus sign. So we can express this labeling process using some kind of Boolean function let's call it CR, that will map any point from the plane to the plus minus, where CRX equals positive if X is inside R and negative otherwise. Okay? So now let's consider, so we want to figure out what this rectangle is. So what would be kind of our naive approach? So naive approach would be, let's try and construct the kind of the minimal rectangle that contains these points. So one approach we will be looking for the tightest possible rectangle, for the tightest can fit all positively labeled data inside. That's denoted as R prime. So this guess, or this approach, in the learning theory is formulated as a hypothesis. We hypothesize that the triangle we're looking for is R prime, so we formulate our prediction function or hypothesis called edge R prime that maps all the points from the plane to plus minus. And if x is in this minimal rectangle, then HR of x is plus, or else HR prime of x is negative. So now with our hypothesis, we can ask the following questions. Question number 1. Have we learned CR? And second question is, how good is our prediction function? HR prime. So let's say that R is the true rectangle, the one that was really intended in the problem, was kind of wired in the problem, that defines the labeling function. CR, yeah? So since we hypothesized that the triangle that we conjecture is the one, is the tightest possible fit, this triangle, this rectangle, sorry, must be fully contained inside R. Must be fully, entirely contained inside R. So we can have our picture. And we'll have a smaller rectangle here. It's easy to convince yourself that this minimal rectangle will be inside R. So clearly our prediction function will make some errors. So let's look at this area here, this gray area here. So the true labeling will label things that are inside the gray area as positive, but our hypothesis will label those points as negative, right? So in this area, here, so H of R prime of x is going to be minus, but C R of x is going to be plus. So our prediction function will make errors on these points. This brings us to a kind of an interesting conclusion, or observation rather, that the data that is used to learn the hypothesis should be similar to the data on which we will be testing this hypothesis. So this brings us to that's why we need to introduce some distribution over the points. So let D be some distribution over points in R2. So then we will call one chunk of data training data. Will consist of M points drawn independently from the distribution D, and then labeled according to CR. So we can now rigorously define what's the error of our hypothesis. We define the error of a hypothesis HR prime with respect to CR and distribution D to be the following function: HR CR D. The probability when X is sampled from D of H R prime of X. All those probability of a mistake. When CR and D kind of are obvious from the context, we'll just write error of HR prime as a function. Okay, so what we would like to do now, we'd like to show that our algorithm that outputs this HR prime is quite a good one, in the sense that given some error epsilon greater than 0, with high probability it'll output a hypothesis such that the error of this hypothesis is going to be less than epsilon. So we will show that we can output HR prime such that for some fixed error epsilon, called the target error, with high probability, it will output the hypothesis such that the error of HR, CR, and D is going to be less than or equal than epsilon. So let's try and visualize what we're going to do. So let's consider 4 rectangular strips. Consider 4 rectangular strips. Let's see if I could draw it. So this is R. This is R prime. And we will consider 4 strips, which will be, this is going to be 1 strip, be the other strip. This will be yet another one. Let's call this T1, T2, T3, and this will be T4. So these are kind of the strips that localize the error, effectively. So they each strip T has a probability mass of epsilon over 4 under D, distribution D. Okay. Some of the strips, as you see, overlap. So we know that the total probability mass T1, T2, T3, and T4 will be at most epsilon. So now we can guarantee that the training data of m points, if we can guarantee that if we can guarantee that our training data contains points in each of these TIs, then we know that the probability of us making an erroneous hypothesis is going to be at most epsilon in this case. So let's try and understand why this is so. I mean, there may be some issues if no points hits a particular stripe, but let's just say that we visit each stripe. So imagine D is a uniform distribution, for example. So consider A1 to be the event. That's m points are drawn independently according to the distribution D, and none of them lies in T1. And we can define A2, A4 similarly. So A4, for example, will be an event where m points are drawn independently from the distribution D, none of which lies in T4 in this case. Okay, so then let's consider the union of these events, A1, A4. If this big epsilon does not occur, then the error probability of HR prime CRD is less than epsilon. But we will see how to show this using kind of some simple elementary mathematical tricks, like union bound. So let's compute P of A1. What's the probability of this event? So the probability of a single, say, point is drawn from D that does not land in T1 is going to be, so let's just write it separately. So 1 minus e to the 4. That's the probability that a single point drawn from D does not land on T. On T1. Then let's try and see what happens when m points are drawn. For m points, because this is all independent, you get 1 minus epsilon over 4 to the m. So we can easily see that probability of each AI is going to be equal to 1 minus epsilon over 4 to the power of m for I 1 to 4. So then, probability of epsilon is going to be less than equal sum over I from 1 to 4 p of ai's, which is 4, 1 minus epsilon 4 to the m, which is then going to be 4 e to the power of minus m epsilon over 4. Where here we just use the fact that 1 minus x less than equal to e minus x. Okay? So now, let's introduce delta, some number, some fixed number. And what we can observe from here, if our m is greater or equal to 4 epsilon log 4 over delta, then we have that p probability of this event is less than or equal to delta. So in other words, with probability at least 1 minus delta, we have that the error function hi prime CRD is going to be less than or equal to delta. So this little rectangle game teaches us quite a lot of interesting things. So what we naturally see appearing here is the parameter epsilon. So we can regard epsilon as an accuracy parameter. And delta, which we just introduced, is our confidence parameter. And you can now look at this bound that I highlight here. And you can see that if we require higher accuracy and confidence, we just need to supply our algorithm with more data. Because you see both epsilon and data in our denominator. If we want better results, we need more data. So this kind of naturally corresponds to our intuition about what learning means and how data improves learning performance. So this kind of little example motivates us to introduce, or motivated perhaps many years ago, Leslie Valiant to introduce a framework that is now called probably approximately correct learning. POC learning. So let's try and kind of define some of the basic notions of this framework using this little insights that we gained from this rectangle learning game. So let's make a few observations. First of all, this is a separate topic. So a few observations. Our end goal is to define very rigorously what we mean to POC learn something, a function, a state, any kind of object. So until we get there, we want to kind of gradually build up to that, introducing as many concepts as we need, but not more. So observation number 1. So the learning algorithm that kind of outputs this hypothesis does not know the kind of the concept, the target concept that is to be learned. Does not. to be learned. Otherwise, there'll be nothing to learn. If they would learn that rectangle, if algorithm knows where the rectangle is, then we're done basically. However, what the learning algorithm does know is the set of possible concepts. It knows that that there's a bunch of rectangles there, and one of them is the one that we're looking for, and we don't know which of it is it. So we need to kind of sample more data and get more and more accurate guess, a better and better hypothesis to be able to approximate the true rectangle. So what else do we observe? So the learning algorithm has access to data drawn from some distribution D. So in order to learn efficiently, it is natural to expect that we have access to data that's sampled from some distribution D. This can be challenged, but in our somewhat rudimentary exposition, we expect that there is some kind of underlying distribution there. So, and we do assume that our observations are drawn independently according to D. However, we don't make any assumption on the distribution itself. We just know it exists somewhere there. The next observation that we have is that the output hypothesis is evaluated with respect to the same distribution D that was used to obtain the training data. And finally, some kind of comes as a sort of as a little remark at the end, but it's one of the most important things. We want everything we do to be efficient in some sense. So we would like, in principle, we would like our algorithms in our case, this rectangle searching algorithm, to be statistically efficient, namely, we want to require kind of a relatively small number of examples to guarantee the accuracy of the data, and computational efficient. So, in other words, we just want to spend a reasonable amount of time to process the examples and produce kind of the output hypothesis. These two concepts are some of the key concepts that we will be constantly mindful of when we introduce various new learning approaches in quantum case. So now let's try and formalize all the concepts that we need for learning. Concepts related to learning. These are the concepts that will feature in the ultimate definition of what it is Pak-learnable, what we mean when we say something is Pak-learnable. So one thing that we need to introduce is something called an instance space. So this is We'll call it x. We say let x denote the set of possible, or the universe of possible instances or example that our learning algorithms will see of possible instances. We want to have an ability to mathematically correctly describe these notions. So we introduce this letter x to denote this, that our learning algorithm will see. That's instance space. Another kind of little jargon that we requires introducing is the concept space or concept class. In back learning literature, that's one of the kind of very first things that you encounter. So a concept C over instance space X is nothing else but a Boolean function C that will map elements from this space to 0, 1. Then we call a concept class capital C over X is just a collection of concepts over X. Of all concepts over X. So in our rectangle learning game, the concept class under consideration is all kind of axis-aligned rectangles. So in order to view the concepts as kind of Boolean functions, in our kind of learning game, we just will use the convention that plus would mean +1 and minus would mean 0 in this case. So I should also mention that the learning algorithm has knowledge of C, capital C, but not of a specific concept. C. That's used to label observations. Okay, so that's the kind of the concept class idea. And next we need to introduce something that will provide us with data, so data generation. To be able to learn, we should be able to get examples. Yeah. So let D be a fixed probability distribution over X. And then the training data is obtained kind of as follows. So we take an example X from X, drawn from distribution D, according to distribution D. And then if C kind of is a target concept, then it's also labeled by the label C of X, 0 or 1. So the learning algorithm observes a pair of X and CX. It knows the point, and it knows the sign of the point in our game. So we will refer to the process of observing this pair as a kind of a process of interacting with an oracle. As computer scientists like to query. We call it a querying example oracle. So we call it X, C, D. It gives us a point and a label. And we will assume that we can submit a request to query this oracle and get a kind of a pair, X and CX. So one thing that we often take as granted, but something that's quite important, is how we represent our concepts. For example, if our concepts are Boolean functions, we have two options. We can either represent Boolean function, say parity, right? Parity can be represented as a kind of as a circuit of n log n gates, or it could be represented as a disjunctive normal form. So it'll be a big, exponentially big table. And both of these objects represent the same thing. The parity function, however, they vastly differ in size. So representation of the concept is actually very, very important. So we need to kind of settle on what we mean by representation when we describe these concept classes. Representation. So kind of abstractly speaking, a representation scheme for a concept class C for C is just a function that takes some finite alphabet and maps it to C, where sigma is just some finite alphabet. So this little star means you get kind of arbitrary long strings. We can form arbitrary long strings from this alphabet. So zeros and ones, for example, it maps to concept classes. So any sigma such that R of sigma, so we'll introduce kind of a function equals C, R being representation, is called a representation. So in other words, there are lots of different ways of representing our concept classes. And we also will assume that there exists a special function called size that will take strings from the alphabet and map them to some numbers. This is all discrete alphabets, so we'll map to some natural numbers here. So this function measures size of representation. Okay, so what we would like to do, we would like to completely remove any ambiguity. We'd like a size function to be minimum of all such representations. So take all possible encodings and minimize them. And that'll be our kind of representation scheme. Good. It looks like we've defined a bunch of things. We're almost there, actually. We're very close to defining what it means to properly pack-learn things. A few other things that's important. So we need to also explicitly introduce the instance size. So we will we'll use X subscript n to just denote all bit strings of size n in our example, and then Cn be a concept class. We want kind of a size dependent notion here. So for every size of a problem n, we have Cn and Xn. So Cn is a concept class over Xn, And then the total instance space X is going to be given as a union of all the instance, kind of the instance space of all the problem sizes. And similarly with the concept classes, C will be just a union of these CNs. So the last thing that we need to define is what it means to be efficiently evaluatable. Because there are two things that we need to keep in mind. One is to be really statistically efficient, so take as little data as possible to make our guesses. And second, we want to be able to actually do it efficiently, so have an algorithm there. So finally, we say that a hypothesis class capital H, so it's a collection of all the hypotheses, is polynomially evaluatable if there exists an algorithm on any input side, any input instance, on input instance X of some size n, and any representation for hypothesis Hn in the class of all hypotheses, such that it outputs value h of x in time, polynomial in n, and size of h. So it's important to be both efficient or polynomial in terms of n, this problem size, and the size of the representation, because we can be silly and pick an exponentially big representation, which would kind of defy the whole idea of efficient evaluation of the hypothesis. Okay, good. So we have everything we need, and now we can define, before a short 5-minute break, we'll define what it means to PAC-learn a concept. So finally, we come to a big and very important definition. It's going to be quite a long definition, but it'll be mathematically very satisfying. So let Cn be a concept class over Xn, and let C be the union of all concept classes for all problem sizes, and similarly X has been the union of all Xn's. So we say that concept class C is PAC learnable, probably approximately correct learnable, using hypothesis class H if there exists an algorithm L that satisfies the following. For all n, and for every element of concept class, and for every d distribution over instances, and for every epsilon between 0 and 1/2 and delta 0 and 1/2, I'll strict here, if L, algorithm L, is given access to the oracle, example oracles C, D, and inputs epsilon and delta, and also size C, all these values, then L outputs hypothesis H from the hypothesis class capital H, such that with probability at least 1 minus delta satisfies the condition that the error function of this probability H is upper bounded by delta, by epsilon, sorry. So we say that C is efficiently Puck-learnable, not just Puck-learnable, but efficiently Puck-learnable, if the runtime of L is polynomial in N, the size of the encoding 1 minus epsilon, 1 minus delta. Okay? When we learn element from concept class C, and if H itself is polynomially evaluatable. Okay, so this kind of requirement that the hypothesis class is polynomially evaluatable is quite a natural one. Ultimately, we want to be able to check our hypothesis in reasonable time. So that's how kind of we started with a simple rectangle example, and we've distilled some of the necessary ideas behind learnability, and we saw how all these many parameters that can be quite overwhelming at the beginning, they come together into this mathematically really elegant definition of Puck learnability. So let's have a short break, 5-minute break, and then after the break, we will switch gears and we will discuss how all this machinery applies to learning quantum objects. We'll start with quantum states, and then we will ramp up the difficulty. You will see that this way of thinking almost directly applies to learning quantum states, because ultimately they're just bigger objects. So let's have a 5-minute break and reconvene at 1:40. instruction, which you can then relax or add or subtract those things. Yes, at the end of this lecture, I will give you kind of like a list of literature, and you will see all of it there, including lecture notes. Classical, yeah, kind of this kind of stuff, perhaps written in a more wordy way, with even more motivations and so on. So the goal here is to try and, where all this comes from. All these weird concepts come from necessity, really. We're not going to talk about other things like BC dimension or boosting and other cool things. It's going to be defined because I would need a whole day to do it. But yeah, I think this will be just the minimum. It will be just about enough for you to kind of be able to appreciate one side of things.
What is the word after polynomial, the last one?
Evaluation. Or even a weird.
Okay, sorry. Yeah, also I have another question. So I'm assuming more from AI side. So that there are actually a recent paper saying that the AI side is more about all of the distribution generalization. So is it possible to formulate within the SimCity framework?
Possibly. I think some people are working on it.
Yeah, and also from the papers like Open and Talk statement by Saskia and Open9 and DeepMind, we are seeing that the learning process is actually a process of impression. So if we come to replace this definition of probability distributed here with algorithm,
Sort of, not quite, but there's a you'll see where this, like in quantum physics, you will see more of a compression aspect to this. Certainly. It's kind of like a lower bound. But yeah, it's true. I could have been written more explicitly. But then you'll have to talk about training data, the evaluation and so meaning, you can learn if you have a limit on data, learn in finite time. Part of the bound is a polynomial, which is the polynomial. So efficiently means approximate polynomial in all its parameters. Especially one of our one else. What is this? You want to poorly.
That's good. The other question like about this statistical efficiency. What is this? Can I give an example?
Yes, so you want to kind of be able to translate use a simple model of training samples.
Small some complex stage.
In fact, in the next example, you will see how algorithm supervised started, yes. All right, let's carry on. So I gave you kind of the very basic definition of kind of pack learnability that you can extend and improve and kind of use it in whatever context you want. I wanted you to, I did this to kind of to see how some of these core concepts really motivated the current push kind of when it comes to learning kind of quantum objects, broadly defined. So instead of learning Boolean functions, or classical Boolean functions, we may want to learn something about quantum objects from classical data. What sort of quantum objects? Well, quantum states, quantum circuits, all kinds of quantum processes, both statistical and dynamical, from classical data. You may also want to ask, well, what if you, given an opportunity to observe quantum data, perhaps even some states in superposition? Again, that's a topic of separate lecture, actually many separate lectures, and this is by far one of the most active fields or subfields in kind of quantum machine learning, or at least its theoretical corner. So I want to start from a kind of a question that posed by Scott Aronson in 2007, in one of his papers that he wrote in that year. So he asked the question, kind of innocuous question, but it turns out that it jump-started the whole subfield. So how well can a quantum state ρ described as a vector or density matrix ρ be learned from measurement results? So in other words, we have some source that emits, say, identical copies of state ρ, and we want to learn as much as we can from it. And we can measure the state using some simple two-outcome measurement, and we want to learn something about the state. So let's assume that for each measurement we're given kind of a fresh copy of state ρ. And what's the aim? Our aim is to obtain a classical description of a quantum state so let's call this classical description sigma, such that it is close to ρ. Here I should qualify that not all measures of closeness would work if we want to be efficient. Let's just say under a certain measure of closeness. So, well, the first obvious measure that comes to mind is when this measure is trace distance. Trace distance between two states. Then the process of getting accurate classical description from a quantum state by means of, well, measuring it, it's called state tomography. And those who know something about the state tomography, they know that this is a remarkably inefficient process. So in general, you have an n-qubit state rho. Well, some kind of a Hermitian 2 to the n by 2 to the n matrix with trace of rho equals 1. And hence it's described roughly by 2 to the power of 2 times n real parameters. So let's let's focus for the kind of a simplicity. Let's restrict our attention to two outcome measurements. Restrict our measurements to two outcome measurements. E1, they are typically described by some operators E, positive semi-definite operators E, and identity minus E. So think of this as kind of E1, this is E2. You have two outcomes. So the probability of measurement kind of yielding the first outcome is going to be given trace of E1 rho for state rho. And so what do we know about two outcome measurements? Well, two outcome measurement gives you one bit of information about the state, right? Each two outcome measurement gives you kind of roughly one bit of information. You can think of them as kind of 0 and 1. So you need kind of roughly 2 to the power of 2n measurements to recreate kind of a high fidelity, perfect, I guess, classical copy of the states. In other words, we need 2 to the power, kind of phrasing it in our language, we need this many measurements to learn sigma that is close to rho in trace distance, or we could use Frobenius norm, all kinds of distance measures. And not long time ago, around 2016, 17, it was shown that this is not just a sufficient but a necessary number of measurements that you need to make in order to kind of recreate this kind of faithful representation of rho in trace distance. So this is bad news, obviously. 100 qubits, this is completely untenable. So what Aronson did in 2007, he showed kind of an interesting kind of PAC-like result. So Aronson showed an efficient PAC-like result that states colloquially the following: from roughly of n, n is the number of qubits, measurement results with the measurements chosen as IID, in IID way, according to some unknown distribution D, on the set of all possible two-outcome measurements we can construct an n-qubit quantum state sigma that roughly has kind of the same expectation value as the original raw for most two-outcome measurements. Not all. So again, in the kind of the latter qualification, most kind of is measured under the same distribution D that generated the measurements. Just kind of in the normal PAC setting, when sort of an approximate correctness of the learning hypothesis is evaluated under the same distribution D that generated the examples. So what's interesting about it, the output state, sigma, can then be used to predict the behavior of original raw. On these two outcome measurements. And it will give a good prediction for most measurements. Good in a very rigorous way. I'll state the theorem shortly. And it will give a good prediction for most measurements, for most such measurements. Okay. So, in other words, of n rather than some exponential in n measurement results suffice for what has been dubbed as a pretty good tomography. So his theorem precisely states the following. So for every epsilon, delta, and gamma, so we introduce yet another constant, greater than 0, there exists a learner, an algorithm in other words, with the following property. for every distribution D, on this set of two outcome measurements, given that T is n times poly 1 over epsilon, 1 over gamma, and log 1 over delta, I should say, given this many measurement results, all in kind of in our familiar pattern, E1, B1, all the way to ET, BT, just like in the kind of standard Pack learning, where each EI is drawn IID from distribution D, and BI is just is a bit with probability BI equals 1 to be given by all the measurement itself, trace EI rho. So given this many measurement outcomes packaged in this kind of way, measurement and its outcome, packaged it as kind of as a pair with probability greater or equal 1 minus delta, the learner produces classical description of state sigma such that probability of trace E, I guess where all the measurements are drawn from distribution D, probability E sigma, trace of E sigma minus trace of E rho greater than gamma, is less than equal to epsilon. So in other words, we see that having this kind of setup, we can construct a classical description that does pretty well when measurements are drawn from this distribution D. So as you see, kind of the approximate correct motivation of original Pack learning, Pack model that we saw in the previous hour, is now quantified by two parameters, epsilon and gamma, where gamma quantifies kind of the deviation from zero. Because kind of the output state sigma now is deemed to be approximately correct if kind of the value of trace of E sigma has kind of additive error at most gamma. So it's going to be trace of E sigma plus minus gamma compared to the true value, which is trace of E rho. Okay, so one thing that is perhaps easy to miss, but there is some important remark that I want to make here. The theorem only discusses sample complexity of the learner. So it only concerns the amount of data that is required. It says nothing about the other part, the computational efficiency of reconstruction of the state. So the theorem only discusses sample complexity. i.e. the number of t, the number of measurements results that we use to construct, and not the time complexity. Typically, time complexity, you can construct examples where it's horrendous. It's very bad. It's exponential. So that's that's an interesting take. Statistically, it's very good, but algorithmically, in general, we cannot say much. Which brings me to kind of another notable result that that was developed much later. It was developed in, I think, 2018, if I'm correctly, if I'm correct. So how do we combine the statistical efficiency with algorithmic efficiency? Well, we have to make some assumptions on our states. We can't just, yeah, question.
So how does the theory prove the sample complexity? There must be some knowledge of the time complexity.
I think it's, yeah, I think, okay, maybe we'll discuss, I'll show you how this proof works, but it's true, and but it doesn't tell you, it doesn't guarantee polynomial scaling of the time complexity. That's the important thing. And I want to provide you with one very interesting and relevant case where you can have both efficient sample complexity and efficient time complexity when you learn certain families of states now. So let's discuss kind of a very notable result. So just to go back, this 2007 result opened really a floodgate of a lot of interesting works that started to investigate how far we can push this, and it gave birth to lots of new ideas in the next decade. So it was a very seminal work that really effectively gave us all the wonderful things like shadows, new ways of doing tomography, and the whole wonderful and very intense research field, very high-profile research field of quantum learning. So in the remainder of our time, I want to kind of mention that there is there are still interesting results. You can still say something about computational complexity if you are willing to make some assumptions on this kind of family of states that you're learning. So I want to talk about PAC learnability of stabilizer states. So many of you may be familiar with the stabilizer states and their remarkable utility and significance in studying foundations of quantum computing, error correction. They play a major role in other models of computation, like measurement-based quantum computing. They're super important when it comes to verification and benchmarking. So let's just have a brief description of what the stabilizer states are. I'm not going to give you kind of a full description, but stabilizer states are basically states that are produced say from 0 to n by Clifford circuits. So Clifford circuits are circuits made up of three types of gates: Hadamard's, phase gate, and CNOT. So you hit all zero state with a bunch of Clifford gates, and you get all kinds of states which we call stabilizer states. So there's a kind of a distinctive feature of stabilizer states, is that they, despite the fact that these are kind of exponentially, long vectors, right? Because a pure state on n qubits has 2 to the n amplitudes. Turns out that they admit very succinct classical description. So distinctive feature of stabilizer states is that an n qubit stabilizer state can be completely described, but is completely described, I should say, yes. By listing n generators of its stabilizer group. So these are kind of generators in the form of plus minus n-fold tensor product of Pauli matrices. So in 2018, Andrea Rocchetta proved the following interesting results. Well, he considered kind of the following setting. He considered stabilizer states. Let rho be the n-qubit stabilizer. N-qubit state, let's say, n-qubit state, stabilized by some non-trivial stabilizer group, by a non-trivial, so nothing, it's not just some kind of identity, or, something that has one element or something like this, non-trivial stabilizer group. S, or subgroup S. So if the size of the stabilizer subgroup is to the power of n, then we kind of defines a pure state. So given a training set now, given a training set T of pairs EI, oops, don't know why it's doing that. Sometimes just disappears. EI and trace of EI rho. I is, you have M of these samples. They're, oops, just gonna page. And this is drawn from some unknown distribution, probability distribution D. And what we want to do, we want to, given this training set from some unknown distribution D, we want to kind of predict, we want to predict the expected value of a new measurement it's called E prime, which is also drawn from D here. So in kind of a succinctly, the Andrea proved the following theorem. It says the following. So let V be a set of n-qubit quantum states and M be a set of measurements and again we have D as a probability distribution over a set of measurements over the set M. Then the concept class Q, which is given by QP, maps measurements to real interval 0, 1, such that a state, so Q sub rho is, I'll explain what Q sub rho means in a second, is efficiently Park-learnable with respect to D when V is a set of stabilizer states on n qubits and M set of measurements associated with the Pauli group, Pn. Ultimately, they're just projections on the eigenspace of each n-qubit Pauli. Measurements associated with the Pauli Pn. So we can say that the stabilizer states, in other words, are efficiently Park-learnable with respect to the Pauli group. So I guess one thing that remains to be defined, Q sub rho of EI is just trace of EI rho. It's kind of the usual outcome 0 or 1 in this case. So what it says, it basically, his results shows how to kind of reconstruct an object that allows you to predict the outcome of some new Pauli measurement drawn from some distribution D. And you can do this efficiently. It's kind of an interesting work, and I think it merits kind of further discussion. But ultimately, there's a lot of effort now to try and understand what classes of physically relevant and well-motivated quantum states are efficiently learnable. There are other. One of the curious things about Clifford groups and stabilizer states is, of course, the circuit that prepares the state is classically efficiently simulatable. State has classical efficient description, so perhaps it's not that surprising that you can learn the states not only efficiently in statistical sense, but also in a computational sense. So you may ask, what other interesting families of quantum states that emerge as a result of application of some very well-defined quantum circuits? Think of, match gate circuits, for example, or circuits that have to do with IQP computations. There are lots of interesting physically relevant circuits that also have classical simulability features to some extent. Some are classically simulatable right away, some under certain conditions. Is this true that states that are prepared by the circuits also always admit classical efficient learnability? And of course, people didn't just stop by studying the learnability of states. People wanted to understand what happens. Can we learn circuits? Can we learn classes of circuits that were applied to a state? Let's say you have a unitary that is promised to be made up of certain gates. Can you efficiently learn that unitary operation or not? That's the whole big field that's hyperactive at the moment. And I would like to perhaps to conclude gradually by kind of discussing some of the open questions that arise in this context. So you saw how kind of classical Park learning arises as a kind of a natural set of requests or requirements on learnability, and how it sort of manifests itself when it comes to quantum learning of states. So there are a bunch of kind of interesting questions that people are looking into. For example, we want to perhaps relax some of the measures of goodness of our replicas. What if we don't want kind of worst case or average case goodness? What if we have some perhaps application-motivated distance, or perhaps we want to preserve a particular property of a quantum state. What can we say about Pak learnability of states and circuits under kind of weaker conditions of distance or error models? There are many, obviously, practically relevant error models that the theorists are not particularly familiar with, and there's a lot of work done to try and understand how this difficulty of learning, both in statistical sense and in computational sense, how it scales, how it behaves under these conditions. Of course, there are other questions that have to do with the kind of verifying what circuits, this Pak learnable circuits did. So imagine you have a hypothesis, you have a kind of an idea what the circuit is, and this is all done in sort of a very idealized conditions, assuming your circuit is made up of unitaries. In the real world, of course, you have noise, you have decoherence, so your circuit is not really a unitary circuit, but it's some kind of a quantum channel. So there's some kind of leakage to the environment. Things become a lot more messy. And there's been, obviously, quite a lot of work in the last year and a half to try and understand what happens there. Can we efficiently verify this like learnable or learnable circuits? There's been, recently, there's been a lot of work done for a particular set of quantum circuits. So there's, some of you may have heard this shallow quantum circuits. This is kind of a constant depth quantum circuits that were originally, that rose to prominence around 2016 by Brave, Gossett, and Koenig, who showed that there's a constant depth, there's a problem, a relational problem with respect to which a constant depth classical quantum circuit outperforms unconditionally, which is a rare thing in complexity theory, unconditionally outperforms the classical constant depth circuit that solves the same problem. So BGK, Brave, Gossett, and Koenig showed this unconditional separation of two complexity classes that now have the quantum complexity classes called shallow quantum circuits, or constant depth circuits, I suppose. And these circuits have recently been shown to be learnable, both from a statistical point of view and also from the kind of algorithmic point of view. And this is results of early this year, actually, by, I think, Robert Huang and collaborators. I think it's either early 2024, or perhaps just a very, very recent one as well. So this kind of circuits become they're very popular. We want to understand more about their kind of behavior, their other facets, not just classical simulability, but learnability and other things. And of course, there's a big field now, it's a big industry of learning, not from classical examples, where you are given a bunch of classical data points and you want to learn measurement outcomes, but what if you're given quantum states as examples? So you have some kind of state in superposition or mixture of superpositions, and you can measure the state, and you can learn something from it, or you can kind of process the samples in some kind of collective way, perhaps. So there's, as I say, there's a big industry here that tries to understand limits and opportunities of learnability, as well as whether models of access models that are proposed are realistic or sensible in that case. So I would like to kind of perhaps leave with a bunch of references. I hope I was able to kind of provide you with some intuitive motivation as to why learnability is an interesting concept and why this is not as difficult as it may seem, especially if you sort of start from very basic ideas and then kind of gradually build them up, make them a little bit more and more sophisticated. So here you can see a lot of kind of a completely non-exhaustive list of recent and not so recent works in this field. I would recommend this nice survey of quantum learning. It's not up to date, perhaps it's 2017, but still very useful. And the recent results by some authors, possibly even in this audience, is that I found this one particularly interesting, is that Clifford circuits cannot be, so you think, okay, stabilizers can be Pack-learned efficiently. What about the kind of the Clifford circuits, circuits that prepare the states? Turns out that they cannot be properly Pack-learned it's a paper by Liang in 2023, unless RP equals NP, which is some kind of a, we don't really believe that that's the case. So, even though we have classically simulatable circuits, the relationship between classical simulability and learnability is a little bit more, more complicated than you would think. And yeah, there's been a lot of great and somewhat overwhelming number of works that discuss all kinds of cool techniques of processing classical information to make some very sophisticated inferences about the properties of a physical system, especially when you allow together kind of polynomial many samples in the size of the system rather than kind of exponentially many. There's been a remarkable number of works in the hundreds by now in the last, I guess, 8 years or so, and counting, of course. So these two works, they are kind of foundational, and they kind of describe some of the core classical concepts. So Leslie Valiant in 1984 introduced kind of the theory of the learnable, where he introduced this Pack learning model. Quite a remarkable set of ideas that he laid out in that paper. And then Kearns and Vazirani have a nice book that discusses all aspects of classical learnability, something that I recommend to kind of skim through before you kind of try and make sense of what happens quantumly. So that's all I wanted to tell you today. Thank you for coming, and yeah, I'll be around here for questions and yeah, any comments. So, thank you. All right, sure. I mean, I'm happy to either take online or offline questions, anything you like, really. But feel free to come up to me after the lecture. I'll be around this whole week.
So I have a question. Is there any intuition why learning circuits is more difficult than learning states?
I guess, like learning static objects is somewhat easier than learning, the kind of the process. Circuits are kind of embody effectively the process of transformation of quantum information, right, from some starting state to some end state. So learning processes is just kind of inherently harder than learning kind of some collection of static objects. That's kind of my intuition. It's not so, you have to kind of look at very specific examples. I can't give you kind of a very general intuition, because it's all about families of circuits. Different families have different algebraic structures that behave differently. The Mudge gates have this kind of very special properties of Lie group, the kind of a closed commutator that's closed in quadratic span and so on. Cliffords have Gottesman-McNeill theorem and other things that make them all efficiently classically simulatable. And I imagine, there are many other circuit families that have other properties. So you have to kind of look very carefully on the kind of the family that you're studying, that's important to you, and try and kind of go through this exercise and see what happens. I mean, there are some results, I think, by Matthias Karrer and his collaborators that talks about learnability of circuits with bounded size. Kind of very, perhaps, generically described. And so they kind of introduce this kind of analog. They study the analog of VC dimension, the Vapnik-Chernovetsky dimension. They have some kind of pseudo, forget the word, some kind of other figure of merit that describes the difficulty of learning circuits there. So there are some really good attempts trying to understand what happens in general. And I'm not sure if I let it, I think I might have actually did I put it there? Yeah, covariant data, pseudo-dimension of quantum circuits. If you look there, there'll be, it's kind of a nice, very nice mathematical paper that describes general difficulty or perhaps expressive potential of various circuits with implications on its learning.
Any other questions? So I have a very quick announcement. We just heard from catering company. They are unfortunately running a bit late. So originally, coffee break was supposed to start at 2:30, but now it will start at 3 p.m. And that will mean that the next tutorial session will start at 3:30. So there's a half an hour delay. Any other questions for this tutorial? Okay, so speaker is here. Please feel free to catch up with him if you have any other discussions or questions. Thank you.